Hello, I'm going to present the paper Stretching Demi-Bits and Nondeterministic-Secure Pseudorandomness by Iddo, Tzameret, and myself. Let's first talk about some origins. As we know, P versus NP problem is an essential open problem in both computer science and mathematics. That is, of course, not an easy problem. At some point, people started to think about if we can find an NP-complete problem and show it is not in P/poly. That is, if we can separate NP from P/poly. A positive answer will resolve that famous problem, the P versus NP problem. To separate NP from P/poly requires us to establish a very strong circuit law bound. Some weaker ones have been established by various methods, and a very fruitful class of methods is called the combinatorial method. Another name known for this is the method of natural proofs. How does it work? Rodborough and Roddick summarized this approach in their paper. The core thing involved in a natural proof is called a natural combinatorial property, or just a combinatorial property for short. If we have a function at hand, by a function here, I just mean a family of Boolean functions, and we want to prove some circuit law bound for this function, we first spot a combinatorial property of this function, and then we show whenever a function or problem has this combinatorial property, then it's hard to compute. Namely, it can't be in a certain circuit family. But the bad news is P/poly natural proofs useful against P/poly does not exist if we believe strong pseudorandom generators exist. What are strong PRGs? Strong PRGs are just generators which generate pseudorandom bits from shorter seeds, and they are safe against all efficient distinguishers, efficient deterministic distinguishers. That's what strong means here. The assumption that strong PRGs exist is a very convincing one, because we do use pseudorandom generators in practice, and they are also safe in practice. I want to explain the two P/poly here. The first one means we can check whether a function has the spotted combinatorial property in P/poly, namely efficiently. Useful against P/poly means whenever a function has this property, it cannot be in P/poly. This theorem claims that a large class of natural proofs cannot exist at all based on this convincing assumption. Something may be even worse. A larger class of natural proofs cannot exist, which is NP/poly natural proofs. If we assume something stronger, the stronger assumption is superbits exist. Then we want to ask, what are superbits? They are also just pseudorandom generators, but this time they are not only secure against all the efficient deterministic adversaries, but also all the efficient non-deterministic adversaries. This is a stronger, possibly much stronger assumption. The second theorem in this slide here is also possibly a very first theorem which touches on non-deterministic-secure pseudorandomness. What did we do in our paper? Overall, we have developed the theory of pseudorandomness secure against non-deterministic adversaries in the cryptographic regime, which means the adversaries can have more resources than the generators. That's what we mean by the cryptographic regime here. In particular, we resolved an open problem proposed by Roddick about the stretchability of a candle pseudorandom generators called Demi-Bits. It turns out that the study of non-deterministic-secure pseudorandomness connects with many other things, such as extending barrier results, average case complexity, proof complexity, and pack learning. Let's now introduce some preliminaries. We say a generator G is secure against a circuit D of set S if this inequality here cannot hold. That is, D cannot distinguish a meaningful portion of truly random bits from pseudorandom ones. Strong PRGs are just generators secure against all poly-size circuits for all large enough input sizes. We want to ask what happens if D is non-deterministic, if we allow D to be non-deterministic. Then D can easily break a generator in the sense above by a simple seed guessing method. D guesses some seed X and tests if G of X is equal to Y. If so, D outputs 1 and otherwise 0. So, to take non-deterministic adversaries into consideration, we have to change this definition. And Roddick has done this for us. A non-deterministic adversary D breaks a generator if it can fulfill this new inequality below. Otherwise, we say G is secure against D. Now, this time, D cannot do this job by just conducting a seed guessing, because D is asked to confirm truly random bits by outputting 1. Hence, if we look at this inequality, we will note that we cannot put the absolute value sense or change the order of this subtraction here, because either will make this task trivial. And the superbits are just pseudorandom generators secure against MP/poly. We can understand the word super here as super secure. They are more secure than standard strong PRGs. Demi-Bits, also proposed by Roddick, are also pseudorandom generators secure against MP/poly, but secure in a slightly different sense. This time, if we want to say an adversary D breaks G, D must be one-set error-free. Distinguisher D must reject all pseudo-random strings. So D has to fulfill a stronger sense. Now, I want to give you a minute or a second to think about the question. Which is more secure, a demi-bit or a superbit? A superbit is more secure, as if no adversaries in MP/poly can break G in the weaker sense, then they of course cannot break G in the stronger sense here. Therefore, a superbit is also a demi-bit, and the existence of superbits is a stronger assumption than the existence of demi-bits. What was known before our paper about non-deterministic-secure pseudorandomness? In fact, not very much. The definitions of superbits and demi-bits, of course, and the theorem that MP/poly natural proofs useful against P/poly do not exist, supposing superbits exist. That's what we know. The proof of this theorem relies on the stretchability of superbits. We know that we can increase the stretching length of superbits, which is the difference between M and N in this slide. We know that we can increase the stretching length of superbits from 1 to something polynomial or even exponential if we are to construct pseudorandom function generators secure against MP/poly. The stretchability of superbits and also strong PRGs can be proved by a so-called hybrid argument. But before our work, we didn't know if we can stretch one demi-bit to 2 Demi-Bits. That is, we didn't know if we can increase the stretching length of a Demi-Bit from 1 to 2. We didn't know that. Because a standard hybrid argument won't apply. Now, let me introduce our contributions in more detail. We developed the theory of non-deterministic-secure pseudorandomness from the following perspectives. We first show that Demi-Bits are stretchable. We can prove a sublinear stretching. We also give some direct applications of Demi-Bit stretching. We propose a definition of supercores, which could serve as a non-deterministic variant of hardcores. And we also characterize non-deterministic security by supercores and also by unpredictability. This is our first theorem. Every Demi-Bit B of stretching length 1 can be efficiently converted or stretched into Demi-Bits G for any constant C less than 1 here. This answers Roddick's open problem 2. Can 1 Demi-Bit be stretched even to 2 Demi-Bits? Why is stretching Demi-Bits interesting? Because it is a first step towards Roddick's open problem 3. Given a Demi-Bit, is it possible to build pseudorandom function generators with exponential demi-hardness? And this is a step to open problem 4. Does the existence of Demi-Bits rule out NP/poly natural properties useful against P/poly? A better understanding of the stretchability of Demi-Bits also sheds light on Roddick's open problem 1. Does the existence of a Demi-Bit imply the existence of a superbit? In addition, we have found some interesting applications to average case complexity and to proof complexity. Now, let's have a look at this stretching algorithm we are going to use. The stretching algorithm itself is extremely simple. We just chunk the given seed into as many equal length subseeds as we need, and we stretch each subseed. The difficulty here is not the algorithm itself. It is to prove the correctness of this algorithm. Namely, is to show the new generator, the stretch generator, is still secure. Is to show it still has a superpolynomial demi-security. Now, let's look at a picture of our proof. We suppose for a contradiction that D is a qualified distinguisher for the stretched generator G. And then we wish to construct a distinguisher C which breaks B. The standard hybrid argument won't apply here, mainly due to the one-set error-free requirement on C. You can see it if you have some familiarization with the hybrid argument. So what can we do? Based on D, we construct a new distinguisher D prime, which exploits non-determinism in a pseudo-random structure keep manner, and we then apply the hybrid argument to D prime. Then combined with some other tricks, we will eventually be able to construct the desired C. This is an interesting proof. I hope you can refer to our paper for more details. As I mentioned above, we also mentioned some interesting applications to average case complexity and proof complexity in our paper. I'm not going into details here. Let's go to the next thing. We propose the concept of supercores, which can serve as a non-deterministic variant of hardcores. Let's first recall what a hardcore is. B in P/poly is called a hard core of a function f if there does not exist an algorithm in P/poly, a polynomial P, and many input lengths such that this inequality holds. That is, given f of x, we are not able to efficiently predict b of x. In the deterministic setting, the theorem is there is a hardcore B of some length-preserving one-way function if and only if there is a strong PRGG. We propose a non-deterministic analog of hardcores. You can have a look at this definition, and the definition here is a little bit complicated. It intuitively means a supercore B is secure against both predictors in MP/poly and co-MP/poly. And we prove that there is a supercore B of some length-preserving function f in P/poly, if and only if there is a superbit G. There are many known equivalent characterizations of the existence of strong PRGs, but this is the first equivalent characterization of the existence of superbits. We can also characterize superpolynomial non-deterministic security in terms of unpredictability. What is unpredictability in the deterministic setting? That means we cannot efficiently predict the next bit given a prefix of a pseudorandom string. We cannot efficiently predict in any deterministic way. We know that an ensemble is strong pseudorandom if and only if it is unpredictable. We can also characterize superpolynomial non-deterministic security by non-deterministic unpredictability as in this graph. Let's look at the graph. Superpolynomial non-deterministic hardness is sandwiched between two new concepts called cup unpredictability and cap unpredictability, two new natural concepts named by us. Cup unpredictability here means the capacity of being unpredictable by predictors in the union of MP/poly and co-MP/poly. And cap unpredictability here means the capacity of being unpredictable by non-deterministic function computing predictors. MP/poly unpredictability, unpredictable by MP/poly predictors, and the co-MP/poly unpredictability, unpredictable by co-MP/poly predictors, are also sandwiched between cap and cup unpredictabilities. And those non-deterministic unpredictabilities are all stronger than the deterministic P/poly, P/poly unpredictabilities. But we don't know if any inequalities here is strict, so it's still an open problem for this. Okay, that's the end of my presentation. Thank you very much for listening.